We're surrounded by stuff that's always moving. Water in our pipes, the very air we breathe. But think about this. How in the world do you measure something you can't really grab onto? I mean, seriously, how much water is zipping through the pipes under your city right now? Or how fast is the air rushing past a jumbo jet? Getting these numbers right isn't just for fun. It's absolutely critical for engineering, for safety. And the way we figure it out, it's actually pretty brilliant. So, the secret, the key to measuring all this invisible movement, it all comes down to one single fundamental idea in physics. It's this one simple rule that, believe it or not, governs this incredibly complex world of flow. And here's the big idea. It's what we can call the speed-pressure trade-off. Sounds fancy, but it's super intuitive. When you force a fluid, like water or air, to speed up, its internal pressure actually drops. Get that? Faster speed, lower pressure. This simple trade-off is the secret weapon engineers use to measure flow in all kinds of genius ways. All right, so let's see how this actually works in the real world. First up, let's look inside a pipe. Say we need to know exactly how much water is flowing through it. Turns out the trick is to give that flow a little squeeze. And right away, you see a classic engineering problem. You've got the Venturi meter, it's sleek, smooth, super efficient, but yeah, it's gonna cost you more. Then you have the orifice meter, which is basically just a simple plate with a hole in it. It's cheap and easy, but it's way less efficient. But here's the thing, they both do the same job. They squeeze the water, force it to speed up, which, you guessed it, causes a pressure drop that we can measure. It's the perfect example of that age-old battle, cost versus performance. Okay, that's great for a closed pipe, but what about something like a river? I mean, you can't exactly squeeze an entire river, right? So we have to get a little more creative. We use a totally different method, but it's still based on that exact same physical principle. Instead of squeezing it, we just put a small barrier in its path. These barriers are called weirs. Now, instead of measuring pressure, weirs work by measuring how high the water gets as it flows over the top. Engineers call this the head. And just like with the pipe meters, there are different tools for different jobs. A big, simple rectangular weir, perfect for measuring huge flow rates in large rivers. But that little V-notch weir, it's incredibly sensitive, which makes it way better for getting super accurate readings of low flow in smaller streams. All right, let's leave the ground and take this principle up into the sky, where things get really serious. Because up there, measuring flow isn't just a neat trick. It can literally be a matter of life and death. For any pilot, knowing your airspeed isn't just helpful, it's absolutely non-negotiable for keeping the plane flying. So how do they do it? With this amazing little device called a pitot tube. And its design is just genius. Check it out. One part of it points straight into the oncoming air, measuring what's called total pressure as the air basically slams into it and stops. Then, other little holes on the side measure the normal ambient air pressure around the plane. And here's the magic trick. You just calculate the difference between those two pressures and voila! That tells you the plane's airspeed. And that one number, that single piece of data, is everything. It's what lets a pilot know they're flying fast enough to stay in the air and not stall, but also not so fast that they risk damaging the plane's structure. It's just a perfect, high-stakes example of physics doing its job. So you're probably seeing the pattern by now, right? It doesn't matter if we're in a pipe, a river, or the sky. The strategy is always the same. By cleverly manipulating how a fluid moves, we can take this invisible world of flow and make it something we can actually see and measure. So whether we're squeezing a pipe, damming a channel, or probing the air, it all boils down to that one powerful fundamental relationship between speed, pressure, and, in some cases, height. One principle, so many different forms. It really makes you think, doesn't it? What other hidden physics, what other simple rules are out there right now, quietly running the world all around us, just waiting for us to notice?